Morning, everyone. I'm going to do a video, the first of several, that's going to give you a quick introduction to your real analysis and the topics of continuity, which is the last for this UNV 509 class. Happy Friday. It's Friday the morning, Friday, November 5th, and I look forward to whoever wants to stop in and see me again on Monday. So I'm going to use these slides from when I actually last taught this class. We're going to go through them very quickly and just give you an idea about what are some of the big topics in a course in analysis. So in the first topic, this is your 571 class, you're going to look at properties of the real number system and then the complex number system as it applies to some of those things, those structures that we were talking about last week, vector spaces, groups, rings, fields, etc. So we're going to see this very common proof: the solution 2p squared equals 2 is not rational. In other words, the square root of 2 is not rational. We did that in this class a couple of weeks ago, and you have a similar homework problem that I've given you for this week. But in particular, what this allows us to kind of conclude is that the set of rational numbers is not dense on the real number line. In other words, there are going to be infinitely many holes in the real number line, and those are the irrational numbers. We'll look at the idea of an ordered set. So we'll define a binary relation, which is the ordering relation, less than, that satisfies these properties. So for any two elements, exactly one of the following is true. Either x is less than y, x is equal to y, or x is greater than y. And then for any three set elements, this relation is going to be transitive. Those all the properties that you can choose to order however you wish, but it has to satisfy both of these properties to be an ordering relation. And so then we'll define an ordered set to be a set together with an ordering relation, one that satisfies those two properties. Now, one of the fundamental building blocks for doing all of analysis is this idea of least upper bound, supremum, and then correspondingly lower bound, greatest lower bound, and infimum. So the upper bound is a number or an element such that for whatever ordering relation you have, all of the other elements of the set are less than or equal to that number. So a set could have a whole bunch of upper bounds. There isn't necessarily just one, and that element has to be drawn from the superset S, but it doesn't have to be a member of the subset itself. And you can similarly define lower bound. And it's a least upper bound if it's less than any other upper bound. All right, so again, the least upper bound doesn't have to be a member of the subset itself, but it has to be smaller than any other upper bound. This is an example, if you take numbers of the form 1 over n, then the supremum, this least upper bound, is the supremum is when the least upper bound is in the set itself. The supremum is going to be 1 because 1 over 1 is in the set, and it's the biggest fraction of this form. You get 1 over 1, 1 over 2, 1 over 3. They become smaller and smaller and smaller towards 0. So 0 is a greatest lower bound. The supremum, doesn't have to be in the set, but it has to be this same idea. The supremum is another name for the least upper bound. So the least upper bound is 1, and the greatest lower bound, the infimum, is 0. And neither one of these are actually in the set itself. One of them is in the set, and one of them is not in the set. Too early in the morning for me. And then we look at the least upper bound property, that you can, properties of the supremum, properties of the infimum. We'll revisit the definition of a field with these two binary relations, things that we talked about last week. Here are those axioms of being a field. And these are things that are true about our set of rational numbers: closure with respect to plus, associative with respect to plus, etc. In other words, the set of rational numbers forms a field. And because it's a field, it has these properties. that if a plus c is equal to b plus c, then you could subtract c from both sides and conclude that a is equal to b. This is what allows us to do algebra, is a consequence that comes about of the field property. Because what you could do is just add the opposite of c on both sides and then use the associative property, which were back in these list of things that you could do in order to reach this kind of conclusion. And then we'll throw in this idea of being an ordered field, given that it's a field, and now that you can order the elements within the field and the things that come about as a result of that. And then there are the consequences that come about as a result of an ordered field. And then finally, we can define not finally, but getting close to this, you can define the idea of absolute value. Absolute value is equal to a if a is greater than or equal to 0, and it's minus a if a is the opposite. Whatever minus means in this field, then minus is the opposite. And then you can define the distance as being the absolute value of the difference. And that's important because, if we can define absolute value, we can define distance. If we can define distance, which is always positive, you can define a metric. And if you can have a metric, now you have an additional structure on that space of points. This is the beginning of what we call point set topology. And then there's the properties that come about from the absolute value. Algebraic numbers are numbers that are a solution to a polynomial equation that has integer coefficients. And the question is, are all rational numbers algebraic? And are all algebraic numbers rational? So we'll introduce the rational zeros property that says that that you have a rational solution to a polynomial of this form. If there's a rational solution, it has to be this divisor of the form s over t. Then the numerator has to be a divisor of the term that doesn't have any of the variables in it, and the denominator has to be a divisor of the leading coefficient. You probably teach this in your high school algebra classes, but this is something that kind of tells us whether we have rational solutions to this or not. And in particular, there may not be rational solutions. And this kind of answers the question about, are all algebraic numbers rational and vice versa. Here's that same proof about the square root of 2 being rational. And then we talk about this kind of the way these number systems relate to one another and this density of these different number sets. Facts about the real number system. Some bullet points about upper bound, supremum, and maximum. And some questions to think about. You can read these. You can play this video a little bit slower if you want to spend a little bit more time with them. We get to the completeness axiom, which is this kind of the way in which the rational numbers and the irrational numbers fit together to give you the real number set. Okay, so every non-empty set that's bounded above has a least upper bound. That's completeness. Every non-empty set that's bounded below has a greatest lower bound. That's just kind of the corollary, the other side. And then, this doesn't necessarily apply to a subset of the rational numbers. You can only do this on the real numbers. This completeness axiom applies to the real numbers, but does not apply to the irrational numbers. And the question is, why? All right, so this is up to you to kind of think about. Can you give an example of a non-empty set of rational numbers that's bounded above but does not have a least upper bound? Okay, this is true of the real numbers, but now I'm telling you it's not true for the rational numbers, which means that you should be able to come up with a counterexample of that statement. We talk about the Archimedean property. Given two positive numbers, can we always find a multiple that's bigger than the other one? Well, yes. I mean, you can always kind of get bigger. And this Archimedean property gives the basis of this proof that the rational numbers are dense in R. And what that means is that for any two rational numbers, there's always a rational number in between them. They're infinitely close to each other. You can't separate them. And we'll make that a little bit formal when we start talking in topic 2 of this review series of videos um, about them being separable, separated into different pieces. And this says that the rational numbers cannot really be separated from one another because they're all infinitely close to each other. There's nowhere to draw the line um, in that way. And finally, we just kind of talk about the symbols of infinity. All right, I'm going to end this particular review video. That's a quick overview of some of the topics from week 1 of an analysis course. In the next video, we'll look at week 2.